Hello. Good evening and welcome to our class today. So, today we are going to have a conversation around quality of service concept, that is QoS. And to start us off, imagine of an ambulance uh, on one of the busy highways. All right. Let's take a highway in Nairobi, Kenya, and it's early in the morning, uh, uh, 8 o'clock, and this is high traffic moving towards the uh, CBD, and there's an ambulance that needs to pass over, just from picking a patient, and it's taking the patient to the other side of the town, and what happens? The ambulance is sounding the siren, and the other motorist will have to give way to the ambulance because the ambulance is having an urgency. It needs to take these patients uh to the hospital. All right. Maybe the patient is on oxygen, and so we're going to be giving way to the ambulance even though there's a very, very heavy traffic. So you realize that because the ambulance has an urgency, the other motorists are going to give it way, and they're going to give it priority, and that is the word. All right. The ambulance is going to be given priority of the highway on behalf of the other motorist, and that is very similar to what we want to have a conversation with. Now, ladies and gentlemen, you and I know that we have three types of traffic. Three types of traffic. We have voice traffic, we have video, and we have data traffic. And these three types of traffic, uh, uh, at one point or the other, they are always having some urgency. All right. For example, okay. So let's check, for example, a live video traffic. You're watching something live, or you're having a video meeting with someone, or a video call, or you're just having a normal uh, phone call, a normal voice call with your phone. These types of traffic are very urgent, and they need to be given some priority over the link bandwidth, And so we need to configure our devices, routers and switches, configure them to be able to always give priority to um, such traffic. This is such live traffic, that because then people, if you don't configure some of these protocols or some of these services within your devices, taking, for example, a mobile telephone company, like one of those is Safaricom in Kenya and East Africa. If you don't do that, then your subscribers and your customers are going to be complaining if they have to use their data bundles to conduct online meetings, or to attend meetings, or to attend uh, an interview, a job interview, using the data bundles or using the wireless network, And we remember that during 2020, when there was serious cases of the COVID-19 virus, of the coronavirus, so many meetings were taken online, so many studies were taken online, so many, family meetings, so on and so forth. So many jobs were taken online. And this made our internet service providers to employ more quality of service within their networks, so that urgent traffic, like, live calls, or live video calls, or live streaming, you know, look at our TV stations. BBC is here. In Nairobi, Kenya, we have Citizen TV, we have Nation TV, we have KTN. All of these guys have taken their broadcasting on YouTube online. Okay. And this is part and parcel of quality of service. And so nowadays, even the number of people who are buying newspapers and watching news at exact times at like 7 o'clock or 9 p.m. at night or in the evening have reduced, because sometimes people just want to watch the news. Either they're on traffic and it's already 7 o'clock or 9 o'clock, and they need to watch that news, they need to catch up with it. And so it is important for us to learn today about quality of service. So some of the objectives for our study today includes explaining how network devices implement quality of service. So we'll explain how network transmission characteristics impact quality. We're going to describe minimum network requirements for both voice, video, and data traffic. We'll describe the queuing algorithms used by networking devices, and then we'll describe the different quality of service models. And then finally, we explain how quality of service uses mechanisms, different mechanisms to ensure transmission quality. All right. So let's first by talking about network transmission quality. And we start by looking at how do we prioritize traffic. All right. Now, when the traffic volume is greater than the bandwidth available within our link, okay, then we get into problems here, because we start getting videos breaking or audio uh, uh, calls breaking, okay? And so we need to do what's called queuing of traffic. These packets need to be queued, because if we queue them and we don't have enough bandwidth, then there's going to be some delay, what we call, um, I'll give you that name, just forgot about that name. It's called latency, exactly, okay? So you'll find that new packets will not be transmitted until the previous packets have actually been processed, okay? And as we continue queuing and queuing, the memory within our devices is gonna be having a stress, and packets are gonna be dropped, okay? And what can actually help us to get out of this situation is having quality of service technique, which is going to classify data into multiple queues. And looking at the diagram that we have here, you realize that we have a voice over IP phone is here, calling some voice traffic. We have some financial transactions here, which always also need some urgency in a way. And then we have web pages here. So depending on the level of urgency and prioritization, how do you prioritize these three types of packets? So we have a higher priority queue, we have a medium priority, and low priority queue as well. So what happens is that because the voice over IP has a higher urgency, so we put it on the high priority queue, and then the financial transactions has a medium priority, we put it on the medium priority queue, and finally the web pages, it's okay. I mean, we put them on the low priority queue. So as traffic exits the router interface, assuming this router is been implemented with the quality of service, you realize that we are going to have more packets of the higher priority queue, and you can see them in maroon. So there's one here, there's two, there's three here, there's four, and there's five here. So five packets are urgent. Then the medium priority queue are just three. So one here, two, and three, okay? And then the low priority queue is just one. So what are we saying? That since these packets are for 9, so for every 9 packets sent, 5 of them are of high priority, 3 of them are of medium priority, and 1 of them. So we are giving the link bandwidth uh, to give priority to the high priority queue, median to the medium priority queue, and the low priority queue. And so quality of service basically works like this once implemented within our routers, okay? And by the way, quality of service only happens when the network is beginning to experience some congestion, all right? So let's look at some of these ones here. These terms here, there's a bandwidth, there's congestion, delay, and jitter. So bandwidth basically is bits transferred per second, okay? The amount of number of bits transferred per second. Checking at BPS as the basic unit for measuring bandwidth. Congestion is when there's less bandwidth than the amount of data that needs to be transmitted. So when congestion occurs, then it's obviously going to cause delay in packet delivery, okay? So as you browse, for example, on your browser is going to load more before it can be able to display the content you're requesting. And to the variation of this delay, sometimes it's a bit slower, sometimes so much, and sometimes it's a bit faster. The variation of this delay is what we call jitter here, okay? And so looking at the diagrams down here, we are looking at congestion points within the devices. And looking at the first one, this is what's called an aggregation. For example, we are having traffic moving from, maybe these are PCs here. Let me just zoom this a little bit. Let's say we have PCs here. These are PCs here. And maybe their speed is 100 Mbps traffic. And these PCs are transmitting traffic through the switch. And the switch has to send it out of it, probably to a router down here. And this port is also just 100 Mbps, okay? So we are going to have a congestion because at the point of aggregation, we're having more traffic coming in, and we're having the exit interface is having a lower speed, and so that cannot be able to manage traffic. So aggregation will make this port to be a point of congestion. Speed mismatch, almost here. So for speed mismatch, we have traffic coming in through 1000 Mbps, which is equivalent to 1 Gbps, 1 gigabit per second. And traffic gets out through a lower port speed of 100 Mbps. So this is having a speed mismatch will also cause congestion on this particular port here. And then finally, when traffic is moving from a LAN to a WAN, right? From a LAN to a WAN, the LAN is having, normally LANs have higher speeds, and we have talked about that. And WANs have a bit lower speed. So when that happens, of course, it will cause some congestion at the exit point of our router. Now, so some of those network congestion points are very ideal points for implementing quality of service. So you need to identify which devices and on which point of those devices should we implement quality of service. All right. Now, I want to take you back 23 years ago. I want to take you back 23 years ago. And I want us to have a small survey here. Okay. Checking at how was the dominance of traffic back then. All right. So the dominant traffic back in the 2000s was voice and data, right? And there was more of data and a little bit of voice because people did not have mobile phones, not so many of them. Mobile phones were just starting to come, right? And now normally voice traffic has very predictable bandwidth, and the known packets always arrive, have arrival times. Now, data traffic, on the other hand, is not real time and normally has very unpredictable need of bandwidth. Data traffic temporary could burst, especially when you have to download some very large files or, of course, uploading. And this bursting of traffic can always consume so much bandwidth on your link. Now, lately, video traffic has become increasingly important in businesses, communications, and all that, and a survey that was done by Cisco in 2017, that is through the Cisco Visual Network Index, 70% of the traffic was actually video traffic. And by the year 2022, which was last year, video traffic represented 82% of all traffic. You know, if you, and when we did during the same study, mobile video traffic itself reached 60.9 exabytes per month. And you can tell it, you know, TikTok is here, and, you know, Instagram is here, and Facebook is here, and WhatsApp is here, and the video calls are here, WhatsApp video calls, and, you know, people having meetings on their phone through Zoom, through Google Meet, through WebEx, through all these applications. And so people are, and even if you went to Facebook, there's more video than any other thing. People no longer write those very long excerpts to be read, but they prefer to communicate through video. And you see someone has posted something, a paragraph and paragraph. The culture of reading is kind of going away, and people prefer to be communicated to and to communicate through video and like through words. And that's why I think even the reading industry is going a little bit down. And so this type of video traffic, you know, unlike data traffic, puts a lot of demand on our network bandwidth, okay? So video, voice, and data as the common three types of traffic have to be taken really into consideration, because there's just a lot to be done on them. Now, I want us to look at each of the three types of traffic there, and we start with the video traffic. Now, video traffic normally is very smooth and predictable, but it's very sensitive to delays and dropping of packets. And that's why, for example, if you are making a call over your mobile phone or over an internet call, you realize that if someone didn't hear what you said, they will definitely have to ask you to repeat it, okay? And they'll ask you to come up again. Now, because of this sensitivity to delays and dropping, voice packets receive higher priority than all the other types of traffic, okay? Now, so the voice traffic uses something we call RTP, which is a real-time protocol, okay? And that uses ports 16384 to 32767 to be able to prioritize voice traffic, okay? I mean, even though voice traffic can tolerate certain amount of latency and variations of latency and sometimes lows without any noticeable effect, latency should not be more than 150 milliseconds, okay? And the jitter should not be more than 30 milliseconds. And the packet loss should not be more than about 1%, okay? And basically it requires about 30 kilobits per second of bandwidth. And so as a characteristics of voice traffic, normally smooth, good traffic, you know, it doesn't have a lot of variations, but it's drop sensitive and delay sensitive. And it, most importantly, there's an error here. It uses UDP, not UPD, UDP priority, the user data gateway protocol, that is for voice traffic. And now video on the other side, which is becoming more busty and inconsistent and demanding more bandwidth on our world networks and bandwidth. Now, if you compare with voice, video traffic is less resilient to loss, and it normally has a higher volume of data per packet. And this is because video still has some voice, it has pictures, it has lights, different variations of light. And so because of this, the number and size of video packets varies every 33 milliseconds. And of course, based on the content. It uses UDP port 554, and it uses a protocol called RSTP, the real-time streaming protocol, real-time streaming protocol. It's less sensitive delay and the network traffic. So for latency for video should not be more than 400 milliseconds, and the jitter about 50 milliseconds. Okay, and of course should not be more than 1% for the delays. We realize video traffic requires more bandwidth, about 384 kilobits per second, unlike voice. So video is very busty, which means and very greedy to bandwidth. Okay, comes in large sizes, and it's also drop sensitive and delay sensitive, and it uses UDP as well. It uses UDP as well. Now, over to the last traffic here, which is called data traffic. Now, data applications normally have no tolerance for data loss, and looking at traffic, data traffic such as web pages or emails, it uses majorly TCP to ensure that packets that are lost are actually retransmitted. And we did learn about this at the end of CCNA 1 when we talked about the application layer. No, sorry, the transport layer, where we talked about the UDP and TCP and the differences. So data traffic can either be smooth or busty, of course, depending on what you're doing. If you have to download a very large file, maybe you're downloading a series or a movie or a book or a large file, it will be very busty. Okay, and FTP will always consume so much bandwidth, especially when you are doing that download. So it can be smooth or busty, but sometimes it can also be very benign or greedy at the same time, depending on what you're doing. Like I said, if you're doing some light browsing, it will be very benign and smooth. But if you are doing a heavy download, it will be very greedy on the bandwidth and very busty in terms of the sizes. It's drop insensitive. It doesn't matter whether there's delay or not, and of course delay insensitive. And like I said, it uses TCP. Now, let's have a conversation around queuing algorithms, the queuing algorithms that are available. So we have 4 queuing algorithms, like I had mentioned. The routers normally and switches normally, they when there's congestion, they're gonna put the traffic on the queue and then process it slowly by slowly, okay, to manage the traffic. So network administrators normally become very active when congestion occurs within their network, okay? And so queuing, which is a very, very important congestion management tool, can be used to buffer, which means to store temporarily, to give priority or to prioritize these packets, or even to reorder them before they can be transmitted to the next destination device. So 4 queuing algorithms are available. We have the FIFO, which is fast in, fast out. We have the weighted fair queuing, the WFQ. We have the class-based weighted fair queuing, the CWFQ. And then we have the LLQ, which is the low latency queuing. Okay. Now, let's talk about fast in, fast out, the FIFO. Okay. Now, FIFO is actually a queuing algorithm whereby it has no concept of priority. It doesn't prioritize or classify the packets. So it makes no decision about packet priority. Okay. And so what happens is that all packets are going to be treated equally, whether it's a live video packets, or it is voice call packets, or it is someone doing some light browsing. Okay. So as traffic comes in, all traffic are treated the same way. That's why we say it is fast come, fast served, or fast in, fast out. They come, they go the way they come, or they come the way, or whatever it is. I know you guys understand that. So there's no kind of priority that is offered here. Okay. Now, the second queuing method is called the weighted fair queuing. And in weighted fair queuing, the packets are actually classified or grouped into different flows based on either source IP or destination IP address, MAC addresses, port numbers, the types of protocols, and even the types of service. Okay. And so looking at the diagram that we have here, the traffic is coming into the router, and once it comes in, the different priorities are actually available here. We have higher priority, a medium priority, normal priority, and the low priority. Okay. So if the different types of traffic, let's say these are the different types of traffic coming in, maybe video, voice, data, so on and so forth, it's gonna classify these packets according to, which traffics require higher priority, what requires the medium priority, which one requires normal priority, and then which one requires the lowest priority here. And so using weighted fair queuing after the classification, then the higher priority packets will actually be sent on the link first, followed by the medium priority packets second, and then the normal priority packets will go third, and finally the low latency packets will actually go last. We are just trying to give some priority to these particular packets. Okay, but it's important also to note that WFQ normally is not supported when you are doing some NAP tunneling, which means you are using some VPNs, or even when you're doing encryption, because these features, they modify the packet contents information that is required by the weighted fair queuing. So that's a very important point to understand. Now, that type of queuing method is what is called a modification of the weighted fair queuing, which is called class-based weighted fair queuing. Now, when after packets have reached a limit of queue, then adding more packets is just doing more damage to this device. Okay, and so the remaining packets are just going to be dropped. Okay, and so instead of discarding these packets as they arrive at the tail end, it's important to be able to do something about it. Okay, now the lower end packets are going to be treated equally, and this is not going to differentiate between the classes of service. So the class-based weighted fair queuing, this is what it's going to do. It's going to really group the traffic into different classes. Okay, so we have, of course, the categorization: high priority, low priority, and then high priority, maybe medium priority, and then the lower priority. Once they do that, classification, these are the user-defined classes here. Then those on the high priority are going to be put on the first class, or the class 1. Then those on the medium priority, of course, will go on class 2. And then those on a lower priority, all of them will be taken to class 3. Okay, so these are the user-defined classes, so that after the classing is done, then weighted fair queuing will now do its job. It will take all those who are on class 1 will go first, those on class 2 will go second, and then those on class 3 will go next. So a small modification of the weighted fair queuing. And then we go to the very last one. And the last one, I think this is majorly normally implemented for voice traffic normally. Now, low latency queuing, the LLQ, it's a very strict priority queuing method, and sometimes it's also called PQ, priority queuing. Okay, and it's stricter than class-based weighted fair queuing because in low latency queuing, it selects the delay sensitive packets, and mostly this is could be voice or video, so that they're going to be sent first. Then the remaining packets could now be put into the different treatments of the classes. Okay, so you take, they're like VIPs. Okay, the voice packets or the video packets are going to be put on the queue first. Then you now give preferential treatment to them, and then the remaining packets could now be put on the queue. And Cisco has a very strong recommendation that only voice traffic will be directed to the queue. Okay, and so looking at what is happening here, we have traffic coming into the router. So as the traffic comes in, all the voice traffic are going to be put on their own queue here. All right, and they are put in their own class of priority because they are given a very strict priority queuing. And then the remaining packets could now be taken through the class-based weighted fair queuing and put it user-defined classes here, class 1, class 2, class 3. And then using the weighted fair queuing, they can now be sent out, but the voice traffic will be sent first. Okay, so a special recognition and a special treatment is given to the voice traffic only. Again, I think that's because they have a lot of sensitivity to delay and dropping. Okay, now having looked at the four uh, uh, types of priority queuing, the first in, first out, the weighted fair queuing, the class-based weighted fair queuing, and the low latency queuing, I now want us to talk about quality of service models. What are some of those ways of implementing quality of service? So don't confuse the quality of service models of implementation with queuing methods. So what are the models of implementing quality of service? So we do have three models. The first one is called the best effort, the effort model. And so this model of implementing quality of service, every time you hear of the word best effort, it means there's no guarantee that, there's no guarantee that um, the matter in question will be given a lot of seriousness. So here, best effort, the data will just be treated as it comes, okay? And so there's no guarantee that, that quality of service will be adopted in this case, in best effort. And so all packets will be treated the same, such that an emergency voice, maybe from the hospital, calling a doctor, is going to be treated the same way as someone downloading a digital photograph, right? Or someone sending an email, for example. It has its own drawbacks and benefits, of course. So first and foremost is that the model is the most scalable because you don't actually need any effort. It can accommodate everyone. And its scalability, of course, is only limited by the amount of bandwidth available within the network. And it has no special QoS mechanisms required. And it's the quickest and the easiest model to deploy. Of course, it doesn't have any struggles. As a drawback, there's no guarantee that the packets will be delivered. That is one thing to note. Okay. And these packets they will always arrive only when they can. Okay. Or if they arrive at all, that is. There are no packets preferential treatment, like I'd mentioned, and very critical traffic will be treated the same way as any casual traffic. Okay. Now, the second one is called the integrated services. We call it the integrated services. Now, integrated services is implementation of quality of service, which is always implemented on an end-to-end real-time mode, okay? And so it manages network resources to provide quality of service to different data streams, and it sometimes creates microflows. So it uses what is called the RSVP, the Resource Reservation Protocol, okay? It uses the Resource Reservation Protocol to build blocks to establish and maintain quality of service. So it uses an end-to-end connection-oriented approach, such that each of every communication or each channel of traffic must specify its traffic descriptor and request resources within the network. Okay, so looking at the diagram here, one of the major drawbacks of this protocol is that it requires a lot of resources, because quality of service is ensured from one end to one end, from one node to the other node across the network here. So traffic has to be reserved for each and every communication that is going across the network. So this end-to-end signaling requires so much bandwidth, and that's the only drawback that we have for it. Otherwise, the last quality of service, implementation model, which is called the DIFServ, the differentiated services. It specifies a very simple and scalable mechanism for classifying and managing our traffic. Okay, it doesn't have the end-to-end strategy because it cannot enforce that guarantee. But the host will always forward traffic to a router, which is going to classify the flows into different classes and, of course, provide appropriate quality or service policy for different classes. Now, so the quality of service is not actually end-to-end, but it's actually implemented on a hop-by-hop basis. Okay, and this applies a quality of service, a uniform quality of service across the traffic that is being transmitted from one device to the other. So it has greater level of flexibility and scalability, and this is one of the most common quality of service implemented in most networks. Okay, now having talked about the best effort, the integrated services, and then the differentiated services as models of quality of service, I now want us to talk about some of the implementation techniques of quality of service. And the first thing I want us to talk about is how can we avoid packet loss as a strategy here. Okay, now, like we had already mentioned, packet loss is always as a result of congestion on an interface. Okay, it means there's less bandwidth and more traffic to be transmitted. And most applications that use TCP normally experience slowdown because TCP, it will automatically adjust to manage congestion. And those packets, TCP packets that are dropped, uh, they can cause TCP sessions to reduce the window size. Now, that is not always the same thing with the UDP, okay? And so to manage drop packets in sensitive applications, it's important to at least have some few of these in mind. Number one is that we need to increase link capacity to, and that is of course the capacity on the link or the link bandwidth, to be able to prevent congestion in our networks. Have enough or guaranteed bandwidth, and this is going to of course better manage your traffic, and have enough buffer memories within your devices. So when you purchase your routers and switches, especially switches, let them have enough buffer memories, because enough buffer memories is going to temporarily manage the traffic as they are being processed. Okay, now sometimes the WFQ, the CB, the class-based WFQ and the LLQ could guarantee bandwidth and provide prioritizing forwarding of delay-sensitive traffic. But it's also important to finally ensure that the low priority packets are actually getting dropped. Okay, and this happens through a mechanism we call RAID, the weighted random early detection. And I think this is one of the things that you'll be asked in your exam. What is weighted random early detection? And this is just the act of dropping excess packets of lower priority before congestion can occur. If you realize there are packets that, they're not so much sensitive, they have very low priority, we could drop them, to ease the congestion. And some of the tools that could be used to manage congestions within our network, we have these three categories of tools. We have classification and marking tools, and as traffic comes into the device, the different sessions and flows need to be analyzed to determine what kind of traffic are they carrying. And this traffic could be quality of service traffic, for example, could be, OSPF traffic, could be access control list traffic, could be VLAN traffic, could be OSPF, like traffic like RIP, traffic for dynamic routing protocols. This traffic could include traffic from ARP, for example, or traffic from other protocols within the network, or ICMP or DHCP traffic. So classification and marking of that traffic, very important. Implementation of congestion avoidance tools, very, very important. And so we could allot different portions of the resources as defined by our policy. It could also help to identify how some traffic could be selectively dropped, depending, of course, on the agency. We could delay some of them, or we could just remark some of them for later transmission to avoid the congestion. And like we had already mentioned, the weighted random early detection, the red, is very, very important to regulate TCP data traffic in bandwidth efficient manner before the tail drops could cause queue. And finally, for congestion management tools, it's important that when traffic exceeds the available bandwidth, traffic could be queued to avoid any or to await any resource availability. Like I said, common Cisco iOS-based congestion tools are tools like LLQ, which is strongly recommended by Cisco, and the class-based weighted fair queuing, for other types of traffic. Now, checking at some of those tools, it is important that as traffic comes into the device, whether it's IP traffic or it's, could be web traffic or could be whatever types of traffic, it's important that we follow some of these tools, mark them, and then classify them, mark them. And you can see we have used some coloring scheme here just to give us an idea of what basically happens. For congestion avoidance, it's important to do some policing, and that's one thing that we're going to be talking about. This policing, which is a congestion avoidance tool, and selective dropping. For congestion management, queuing is very important. Put them on the queue, and scheduling for later transmission and shaping. So policing is when you drop excess packets, and shaping is when you delay excess packets for later marking, classification, and queuing. Okay, and so it is important that we have some of these tools in order to be able to manage a quality of service. So, by the way, the configuration of quality of service is beyond the scope of this course, and you find some of these in CCNP and beyond. So here we don't normally configure quality of service, but it is important for us to have an idea of how that happens. Okay, so that makes the end of for this particular chapter.